Hey, AB students, we're on to number 3, the last of the 3 calculator questions. So we're going to highlight some things. Oil's leaking from a pipeline. It's producing an oil slick. So the volume increases at a constant rate of 2,000 cubic centimeters per minute. So that is the rate of change of volume. So that means the change in volume as time changes, and it's increasing, so it's positive, 2,000 cubic centimeters per minute. And then we know the shape is a right circular cylinder. Radius and height are changing with time. So we know the volume, the radius, and the height are all changing with time. It's important. They're all functions of time. And they give you the volume formula for a cylinder. Now we read, let's go to a beautiful, what color should we do? How about yellow? So when the radius is 100 and the height is 5, the radius is increasing at the rate, again, whoa, that's ugly, rate of 2.5 centimeters per minute. So when R, I'll write this, ooh, that's hard to read. Me no likey. Let's go brighter. Let's go to this orangish color. Ooh, that's ugly. Brownish orange. So the radius is changing. dr is changing radius as time changes. And that's going to be 2.5 centimeters per minute. Now, this is at certain conditions. That's when R is 100 and H is 0.5 centimeters. All right, what are they asking for? Let's do this nice green. They want the rate of change, the height. They want dh dt. Your favorite related rates. So we have the rate of the volume, the rate of the radius, the rate of the height given there. And so as h changes, so does the volume. As the radius changes, so does the volume. So all 3 of these are related to one another, but they're also connected with time. Volume changed with time, the radius changed with time, and height changed with time. So as we write this formula, the volume is pi r squared h. Here's what you have to realize. Volume is a function of time. The radius is a function of time, and the height is a function of time. They all change as time changes. So none of them are really variables, they're all functions. So when you take derivatives with respect to time, because that's our variable here, if you look, it's all with respect to time. These 3 things, they're all functions, so you have to treat them as functions. The constant we have is pi. So when we take the derivative of this, you have to treat them as functions, not variables. So if you take the derivative of v with respect to time, clearly the derivative of v with respect to time is dv dt. Ooh, I'm going to do something cool here. I'm going to waste some time. Sorry, guys. But I'm going to eliminate that writing by doing white. White. Is that white? I don't see where white. And I'm going to make this fat. And I'm going to get rid. Yeah. Now, this ain't going to get in the way. Look at that. I am so smart. You guys are so lucky that I am smart. I shrink that down. So the derivative of v with respect to time, clearly, that's dv dt. That's the definition of dv dt. It's the derivative of v with respect to time. So now we have a product. Pi r is being multiplied by h. So when we have a product, I do the product rule. So I'm going to leave the first alone. The pi r squared, I'm going to leave it alone. But now I have to multiply by the derivative of h with respect to time. But by definition, the derivative of h with respect to time is dh dt. Because if you look at that, that's the derivative of h with respect to time. Then I have to take the derivative of the first part. So pi box squared, you move the 2 in front, the pi stays, and it's r to the first. But then you have to multiply by the derivative of the box, which is r. So I need dr dt. And then times the second, so I leave the h by itself. All right, now I just plug everything in and magic happens. We know dv dt is 2,000. That was given. We know r is 100. We know dh dt. No, we don't. That's what we're looking for. So I leave that because we want to find that. 2 pi stays. R is 100. Again, we found this over here. dr dt is 2.5. Watch this maneuvering. Bam. 2.5. And h is right here. Watch this. Woo! Bam. 0.5. So I get 2,000, and that's 1,000 pi dh dt. Okay, I'm gonna use my calculator because I'm not so smart. 100 times 2.5 times 0.5 times 2. That's 250 pi. Now, I'm just going to do my calculator. I'm going to subtract that, then divide by that. And my dh dt hopefully comes out with the right answer. So I'm going to do 2,000 minus 250 pi. And I'm going to divide that by 10,000 pi. 10, oh, let me put some parentheses. 10,000 pi, end my parenthesis. Okay, hopefully this is right. I'm getting about 0.0386. Whoa. Yeah, 66. Which you can write as 0.038 or 0.039 if you round off. Yes! Now, let's read the question, because you always read the question. It does not ask for units, so I don't need the units. Bam! Part A, dunno. We still have part B and part C. So let's keep working here. I'm going to erase all this stuff. Uh-oh, you saw what just happened, didn't you? All that covering of the instructions got demolished. So I'm going to recover this stuff. Let me go white and thick and cover all this. Magic. All right. Shrink this down. Okay, so the next problem is your favorite? You want to know maximum volume. So when you read that, you should know that maximums occur at critical points or endpoints. So let's take a look-see. So we want to find the critical point. The critical point is when the derivative of the amount of oil is 0 or undefined. So I'm going to go a long way here, but you don't have to do this technically. The amount of oil, I will say let this equal A of t equal the amount of oil. So that's going to be the start amount. Does it say that it started? And it really doesn't matter the starting amount because that's going to all disappear. So we're going to assume that the starting amount was 0. Here, let me do this the long way. The start amount plus the amount added minus the oil taken. So how do you find this? We're assuming a start with 0, and again, it's not going to matter. To find the amount added, you integrate the rate at which oil is added, and 0 to t, and the rate is 2,000, and it's constant. I'm going to do a dx. So when you integrate the rate at which something is being added, it tells you how much was added. So I'm going to subtract the rate at which is taken away, and it's 400 radical t, but I've already used a variable t, so I'm going to call it 400 radical x dx. So that is the amount of oil, assuming we start with 0. So we want to know when the maximum occurs. That's when the derivative of the amount of oil is 0 or undefined. So if I take the derivative is 0 is 0. That's why it doesn't matter the start amount, because the derivative, that would always be 0. The fundamental theorem of calculus, one of them, says if you integrate or take the derivative of an integral from a constant to our variable t, because we're taking the derivative with respect to t, because we see it's t here, all you do is plug in t for x, but there is no x, so that's just 2,000. And here, we take the derivative of integral from a constant to t, and again, t is our variable, so just plug that in for x. That's going to be 400 radical t, and we want to know when that's 0, so we pop that in our calculator. You can either put that function in for y1, or we can add 400 radical t to both sides, and we get 2,000 equals 400 radical t. And on our calculator, we graph those two things. And if we do that, it comes out to 25 nicely. Let me see. I find that hard to believe. So I'm going to set my window from 0 to 30. And my y needs to go really big because I have y equals 2,000, so I need bigger than that. So I'm going to go 2,500. Graph that thing. There's my rate of oil leaving. I see the intersection. I do second calc intersect. And exactly 25. That is beautiful. T is 25. So now the endpoints, we really don't have endpoints. 0 would be an endpoint starting time. In the endpoint, there is no end time. So how do you test your endpoints? You actually don't have to here. This is going to be one of those weird cases. So that's our only critical point. So if we make a table, this is t, Oh, 25. This is 25. This is my time. This is going to be A prime. I should have did this a different color. So I'm going to just pick 10 and 30. If you plug in 10, so 2,000 minus 400 radical 10, I will do that. I'm going to show you what's going to happen. 2,000 minus 400, well, radical, okay, 400 radical 10. That comes out to be a big positive number. So the derivative is positive. Then we're going to plug in 30. So I can go back to my last equation, edit it to 30. That comes out negative. So actually, you don't have to check the endpoints. This is one of the cases where you don't have to check endpoints, because think about what's happening here. You have a function from 0 to 25. The derivative is positive, so you know it's increasing all the way up to 25. After 25, the derivative is negative, so it's always decreasing. And since we actually have a theorem, if you have a function with only one critical point, that critical point will be a max or a min. Because look, if it's increasing, then decreasing, right? Then it has to be maximum at that point. It can't be maximum to the right because it continues decreasing. And it can't be maximum to the left because it was increasing, so it keeps getting bigger as it moves to the right. So clearly the maximum occurs at 25. So that is actually a theorem. So since 25 is a relative maximum and it's the only critical point, it has to be the maximum. So there's your answer for that one. 25 minutes is when the maximum occurs. All right, part C. By the time the recovery, I'm going to erase this first because it is a mess. And you know it's going to, yep, there goes my white cover up. Are you sad with me? All right, let's cover it again with white and make it fat, just like me. Okay, let's read. By the time the recovery device begins removing oil, 60,000 cubic centimeters of oil is already leaked. Write but do not value the expression involving an integral that gives the volume of oil at the time found in part B. Okay. Okay, so in part B, actually the amount of oil, there's already 60,000 cubic centimeters before it began pumping. So in the previous question, technically the starting amount would have been 60,000, but it didn't matter because it canceled out. In part B, so we assume there was 60,000. So here's where the formula from the I should have said this. On the previous one, you didn't need that formula A of t because the derivative A of t is just a rate of oil accumulating minus the rate of oil being taken away. So to get the derivative of the amount of oil is just going to be your 2,000 minus R of t. You didn't even need the original. But this one, we're going to go back. Oh, that's fat. Fat. Let's skinny it up. So check this out. The formula we had before, when I said let A of t equal the amount of oil, this is basically what's going on in this problem. So A of t, I guess I shouldn't be lazy, is the starting amount, which they tell us is 60,000, plus any oil that's been added, and it's added at a rate of 2,000 cubic centimeters per minute. And then the pump takes it away at the rate of 400. And since t is used, I use x. Bam. So if I want the amount of oil at 25 from the previous problem, I just plug in 25 everywhere. 0 to 25, 2000 dx, 0 to 25, 400 radical x dx. You just put that in your calculator. Oh, you don't have to simplify, do we? Nope, we're done. We are el dano. There is your final answer. So that's it. And just a note, I'll probably write a memo to everybody if you happen to hear the end of this one. I'm planning some times where I'll just set up a Google Meets, invite everyone to join, and if you have any questions, you can ask questions. We can hang out together. So maybe a couple times next week I'll set some times up, and yeah. So I'm looking forward to that. That's the end of question number 3.